This is AS Further Pure Maths. We are in Unit 4 and it's vectors, and we're towards the end. 4.15, the angle between two planes. So if we have a plane like this and a plane like this, we're trying to find the angle in between. That's our wee theta there. The angle between two planes is the angle between two perpendiculars, one in each plane, drawn from a point on their line of intersection. If you are given vector equations of the two planes, you need to be able to calculate y, x, z. So that's y, x, z theta. So from y, you draw the perpendicular coming out and to the plane ABCD. That's fine. So the perpendicular of this plane here coming out this direction here, and from Z you draw the perpendicular ABEF. So looking from here, it gives us this diagram here. Here is our plane. Here's the other plane, and here are the two perpendiculars coming out. That's why they're at right angles. So this one is right angles to this plane, this one's at right angles to this plane. If you do a wee bit of manipulation, you can see that this theta here has to be the same then as this theta here. This is the normal to this plane. This is the normal to this plane. So if we find the two normal lines, that's nice and straightforward. Find the normals just using the scalar form of the equation of the plane, and find the dot product then between the two. We can find that angle there, if it's going to be the acute angle in between two planes. So this is pretty much what it says here. If the two perpendiculars meet at P, then this one plus this one's 180 degrees, obviously straight line. Theta plus phi is 180 degrees. Since the angle sum of a quadrilateral is 360, blah 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 blah, is effectively saying this angle here has to be the same as this angle here. Where are we getting that from? That's 90 and that's 90. This is a quadrilateral. These two add to 180. But these two also add to 180, so this one must equal this. So if we find this angle here, using the two normals, it's the same as the angle between the two planes. That's what we're trying to find. The acute angle between the planes is therefore equal to the acute angle between the normals of the two planes. If n is a vector perpendicular to the plane ABCD, and if n2 is a vector perpendicular to ABEF, then n1 dot n2 equals the magnitude of n1, magnitude of n2 cos theta. So cos theta is then that, again, where we take the modulus to make sure you find the acute angle. If you kind of think about it, if you two planes just kind of crossing each other, these are planes, one of the angles is going to be acute, one of the angles is going to be obtuse. So if we take the positive value, that will always then find the acute one. These things generally, as ever, make more sense with an example. So let's take a wee look and see what we can find. Alright, so we have this one. So a vector normal to the first plane is, of course, this, because it's r dot n. So a vector that's normal to this is going to be 2, 1, 3. A vector normal to second plane, you've guessed it, is 2, 3, 1. So we can use those. So if theta is the angle between, then 2, 1, 3, just using the dot product formula, dot 2, 3, 1 equals the square root of 4 plus 1 plus 9, that's 14, times the square root of 14 cos theta. Dead easy then. Cos theta equals 4 plus 3 plus 3. Where am I getting that from? That's obviously the dot product. 2 times 2 is 4, 3 times 1, 3 times 1, all over root 14 times root 14, no prizes, gives you, of course, 14. So theta then is cos the minus 1, 10 over 14, or 5 over 7. And the nearest degree then theta is 44 degrees. And the nearest degree.